So my name is Zach Michaels. I'm the lab manager for the Scanning Electron Microscope and Microanalysis Lab that's part of the Arizona Lasercron Center. And I'm going to show you some of the stuff here and then explain a bit about how we help with the whole lasercron process. So right here is our Hitachi S3400N Scanning Electron Microscope. It's a variable pressure microscope, which means that we don't have to coat samples to run them, but we get better imaging when we do. So we tend to coat most of the samples that we do things like CL for, where we're trying to look at high resolution details within grains. It has a very large chamber, which is nice for other applications. You know, we do image some things that aren't just zircons. We can put whole rocks in there. And I will move you guys to show you a bit, but I think you can kind of see back here. This is our CL detector. It's a Gaton chroma CL detector, which means that it detects a few different bands of wavelengths. It is not a spectroscopic CL, so it doesn't cover all the wavelength energies in little bins. It's binned into red, green, blue, and ultraviolet, but we can make RGB images from those, such as the one I'll point out here up on the screen in a minute. And then we also have other detectors that we are starting to use more and more for advanced ALC research applications. And so in general, this is our EDS, which is for mapping chemistry using X-ray energies. And we use that for a lot of applications. But this is our EBSD detector for measuring crystallographic orientation and phase information. And we're starting to integrate this now with more in situ studies for geochronology and looking at phase transformations in interesting phases like bedelite or zircon and rhyolite. So we're integrating ALC with a lot of the planetary science groups in some of those interesting applications as well. It's a bit more crowded in our lab recently because we just got a bunch of new equipment. So as I mentioned, we have these new detectors, but they're kind of old. We recently just got funded and purchased an upgrade for a new EDS, a new EBSD detector from EDAX, and I'm extremely excited about it. It was delivered on Friday. Sorry about the compressor there. It was delivered on Friday, and we're getting it installed next week, right as I get back from GSA. So I'm extremely excited about that. When this shuts off, I'm going to go over to the SEM and show you a little bit more about how we do the imaging related to the ALC samples that we typically process. All right, can you guys hear me okay? Great. That'll stop in just a second. Oh, there it is. All right, so I just wanted to show you because we've been actually pretty busy lately, and I figured I have a sample in here. I could show you some of the imaging that we do. So the two main images that we tend to make for every sample that comes through the ALC, every mount, is a backscattered electron image, which is what you see here. And I think I can make it bigger here. Well, anyway, you can see it, and it's up on the screen here. And the point of the backscattered electron image is that the scattering interaction that happens within each grain only lets a certain number of electrons sort of back to the detector, depending on the density of the mineral. So the nice thing about that is that we can get a qualitative grayscale image for different phases. So when we make something like this, like a detrital mount, we're looking for certain phases in, we'll add rows of standards, as Sarah was talking about, of minerals that we know we're looking for, in this case, zircon. And that will have a certain grayscale level that we can tune the instrument for. So it's kind of an art to get what you think covers, highlights the phase you're looking for, but also allows us to see other phases and grains in there so that we can navigate. And what you'll notice maybe here is, here's our row of standards. I've tuned this to be a pretty bright grayscale, near white. And as we scroll down to the actual sample off the standards, we see that there's a bunch of other grayscale values and grains here, and only a couple that are really bright. And so, you know, this is not our best zircon laden sample, but this is maybe a good example of the BSE. So here I can zoom in and show you that this is a zircon, whereas these other grains are not. And these two different grayscales are probably are different. They are different phases. So what we do is we end up making a mosaic of these images or of this area that makes a whole map. So you can use it to navigate your sample. And that's useful because you want to be sure that you're actually analyzing zircons as opposed to some other phase, not only for your data, but for the sake of the instruments. I'll just point out here that then the other kind of imaging we mainly do is CL imaging or cathodoluminescence imaging. And it's a luminescent type of imaging that's very sensitive to beam current. So we really have to crank the current to get the kind of best images we can. We can do it at lower kV and lower currents, but we end up counting for a long time. But we've been getting really great images lately. And I'll just show you a couple of these. This is, a single grain. This is another single grain showing more complicated internal and metamic areas. And then I'll just walk over to, we have a couple workstations. These are the kind of maps that we'll make from backscatter. This one is a backscatter map, but we'll also make them from the CL maps. And that's what we provide you with to help you pick your spots, navigate your sample, and select grains or areas that you want to analyze. Sometimes after analysis, we'll image the grains as well to look at where the pits were and the context, say, within the chemical zonation that we can see in a CL image. So, most of the time what we do is image the grains or samples before they're analyzed. There are times where it's prudent to analyze them after. So we use the SEM for any imaging we want to do, or as I mentioned, any chemical analysis or phase analysis. Sometimes we get samples and we're not sure what everything in the mount is, and we want to be sure before we're accidentally bumping it with the laser. And so this is our tool for all of that. And every sample that you send to us will get imaged here, unless you've done your own imaging, to provide those maps and those navigational tools for you, and at your disposal if you need any higher resolution local areas of interest that you want to look at. I will also mention that especially now as we're coming out of the COVID era, I encourage any visitors that want to learn to use the equipment and use the machine and learn to do the imaging or shadow or however much you would like to participate, to feel free to reach out to do that. Usually we're just kind of moving through samples here, and I'd gladly coordinate to let you know when we're running your sample. If we're imaging it before you get here and you really would like to see, I can Zoom with you. You can have kind of a remote session with us where we can talk about what we're doing or talk about training or think about when you come here if you want to do some more training. So anyway, we're here for you. These are the tools that we use to image your samples. And I think that's all I really have to say. If any of you are interested in sort of advanced EDS and ESD analyses separate from laserchron sort of geochronology or integrating the two, which is sort of my interest, please reach out in the near future because we're installing this new state-of-the-art system very soon. All right, thank you.
Thank you, Zach. Do we have any questions for Zach in the SEM? All right. I think next lab, I'll make sure your email gets posted somewhere.
I'll put it in the chat.
Hi everyone, this is Yin Wang here. I'm a manager in the new lab, and I'm sorry I had a cold. My voice is a little bit tight, so I will try my best. Speak the tool here in the new lab. Can you hear me well?
We can't hear you very well, Yanling. You might want to turn the camera towards the mass spec and stand a bit closer. to the
Okay.
microphone.
Okay, I see. How about now?
Yeah, that's a bit better.
It's better. Okay, good. Okay, everyone, sorry. This is Yan Wang, and I'm here as a new lab member, and I started in January this year. And this is the lab where you can see when you enter into the lab. So we have the instruments on our left side, and then this is the working station where we select spots and tune the instrument and speak, collect the data. And here we have the data reduction station here. So we can just immediately reduce the data once we get collected the data. And once you come into the lab, you should have your samples ready. Okay, over here, let me show you what we usually get for our samples. So we have these two kind of samples. These are the 1-inch round epoxy mounts, and one of them, this is igneous zircon. So I don't know if you can see clearly. So we have several samples over here, and we have the standards inside. And this is the detrital zircon mounts, and the square in the center is unknown. And we have some standards from the lab on the top and bottom. So once you come to the lab, we have those samples ready, and we can load them into the sample holders here. So we have two kind of sample holders, and this is just a 9-hole sample holder, and this one can hold 9 the 1-inch round epoxy mounts. And this is another one with the slice here. So if you have thin sections, you want to do the UC2 analysis, we can load the samples onto here. Right. So once we load the samples, we put the sample holder into this helix, cell. So right now, this stage is moving, it's analyzing samples. So here you can see, sorry, let me find this best angle here. Okay, so here you can see an arm is going inside of it into the cell. So on the end of the cell is like a cap like this. So the laser, okay, yeah, I forgot to tell about the laser. Yeah, so this is the laser, and this is a photon machine, unlike G2 excimer laser. And so the laser is generated by argon fluoride or neon fluoride. So it's like if you have the sample ready and we have this laser comes through the hole over here and then shoot the sample under it and then collect the aerosol and using this little cap. So it creates kind of like a pressure over here. So draw the samples into the country as a country and into this, the other, get out from the other tube. So this get into the arm over here. And then follow this little line and goes really fast into the torch. So, okay, now it's the new plasma system here. So from this part is the plasma, and once the samples goes into the system, and we cannot see the plasma, but maybe you can see a little bit from the window here. So it goes into the torch. So it goes into the aerosol goes into the torch, and the plasma here get analyzed those aerosol and turn them into the ions. Then the ion beam will just enter the vacuum part of this chamber. So the first thing it goes in the aerosol, it goes through this sample cone. So this is the nickel hole. You can see in the center, that's the 1 millimeter hole. So the ion beam just right go into the sampler hole, sampler cone, and then the skimmer cone looks smaller, and it's just behind the sampler cone, and it goes into the lens system here. So over here we have those. This is the extraction lenses. So we have the beams just go through this hole and then to the transfer lenses over here. This is the transfer lenses. So it goes into the this way and gets focused. So those are all the lenses that help us to get a very like thin, strong beam and goes through those different lenses, and then at the end is the source slit. You can see maybe a little bit over there. That's the source slit that defining the ion, the beam peak. Okay. One thing to notice is so this is the new system is getting like from this part. This is atmosphere, and this is the vacuum. So and the vacuum is about 10 to the -4, and then when it goes to the to the detector part, it the vacuum getting brighter to -8, and then -10 on the detector system. So that allows the beam be accelerated and goes into the system. So after the transfer lenses, the beam will just send into the ESA system, which is over here. So this is like a 120-degree ESA system. This is the electrostatic system. Is kind of like an analyzer, which is helping to kind of like filter the energy, kind of like get rid of those very heavy and very low masses, and then put the beam onto a much focused status. And then it comes into this vector magnet. So this is a magnetic field here. So if like so when the beam comes through, so because the beams they have different masses, they have different size, and they just get deflected by different degrees. Like the heavier isotopes. So for example, the heavier isotopes just go through into the right side of here, like the 20, like the uranium, like 238, 232, and then they just go to this side, and the lighter masses, like the light, go to the left side of this detector. So this detector, we have two different kinds of detectors. One is the Faraday cups. We have 12 Faraday cups, and we have 4 ion counters. The ion counters we use usually use them to measure the low mass, like 206, like 204, 202. So this is the where we get the counts from the detector, and then it will show up in the computer over there. All right, let's move to our working station. Okay. So right now we have in this working station, we have 3 parts, 3 different computers. And right now we are just, you can see over here, on the cross here, we are just shooting the laser on a standard. So we are doing a round robin right now. So which is, we just measure the different standards in 1 month and say how they look like compared to their real value. So right now we are just looking on the FC standard. So you can see like now it's shooting, laser is shooting, it's collecting data. In this computer, you can see. Okay, now the laser stops. So it's really fast. Like when the laser stops, the signal stop immediately. Now it's locating another sample right now, and see this peak. Then it's collecting background. So right now we are doing a 300 analysis per hour. So it's about like couple seconds of the analysis, and then like 5 to 6 seconds for the background. Okay, so over here in the middle one, I'm going to show you a little bit about our cell images that Zach has mentioned in the SEM lab. So we got the cell images or the backscatter images from the SEM lab, and then those are really helpful for us to like even like to just define zircons and locate them and find the best part to analyze to place the slot at. So this is a picture of detrital zircon. You can see over here. So there are lots of twins, and those bright, like brighter one are the zircons, and there's much more than like minerals which are not zircons. So sorry, this. Let me show you this. Okay, this is the igneous rock. So those are the igneous zircons. We can see the beautiful zonings for some of the samples. So once we have this, we know, yeah, like if some researchers, they are focused on the like the old zircon, the core, and they just want to see if there is an inherited zircon from their samples. They can see it clearly from the CL images here. And then they can play the spot in the center and maybe some on the rim, and then just work like what we have been done. So we got the, yeah, even you if like it's the greens are fine enough, you can also like create a line and see the difference between the core and the edge, the difference, and the green edge difference. And so in our lab, so we are very lucky and to have like very like fast analysis right now. So we can do 1,200 analysis per hour. So right now we are doing a 300 analysis per hour. It's pretty, yeah, like in 1 hour, you can get 300 like spots and you got the data. So once you got the age data, like you get the raw data, we can immediately reduce the data in the using the HCalc MATLAB. Oh, okay. Now let's see this a little bit tighter. Yeah, it's catch. Okay, thank you, Mark. Okay, so Mark is helping me to holding the camera. So now we can say this is round robin we ran yesterday, and this is so this is the 6:8 ratio. This is pretty straight, and the 207 is pretty good, and it's close to 1. It's like 1.07 probably. So and we will do the, so what we do is we just like measure the counts of the everything, the unknown and the standards, and then we standardize using like we just compile this data into the like we compare, like kind of like we match the counts and the concentrations or the age or the ratios of the standards, and then we have that relationship of apply that same relation, the factors into the unknowns, and then get the age. And here you see the secondary standard. We got 416.5 millimeters. That's an R33. So the real age is like 419 million years old. So it's like within 1% precision. And I think that's it. Yeah. I think that's it. So we have Sam here, and he can we have another laser system, and he can just discuss, like introduce that a little bit. But if you have any questions, please feel free to ask. Yeah. Maybe research to done.
All right. Yep. Okay. I'm Dan Alberts. I'm a PhD student here, and my main duties are minding the Element 2 lab, which we will go over right after this. And I just wanted to highlight our laser systems here. So Yanling just showed you guys our workhorse of our lasers that we've been using for years here at LaserTron, which is the Photon Machines G2 193 nanometer excimer laser. But we have recently acquired the Iridia laser ablation system, which we can see here. And I have all the covers off of it. And I'll just go really briefly through what the laser is actually doing to our sample, and then highlighting this really new laser that we have, which is the Iridia system. So starting all the way at the bottom, like Yanling had mentioned, we have argon fluorine gas, which is the gas used to have our laser generator. Down in the Iridia system is very similar to the G2. A lot of the stuff I'm going to go over through this laser also apply to the G2, but this is the latest and greatest on the market. So we have in the bottom of the laser cabinet, we have helium purge gas, which we use to fill the laser generator, which is in the back here. And that helium gas is used when you're moving it or leak checking or changing out argon fluorine tanks, which is this guy right here. This gas is rather expensive and difficult to acquire at the moment. But this gas also degrades over time, over 2 years. But using this gas with this specific laser system in here, which is an M-Laze laser, another 193 nanometer laser. After we fill that laser generator with gas, I'm going to rotate us around here real quick. We then go into the beam path. And from what we have in here, it gives us a pretty good look of the exact same geometries that are happening in our G2 laser systems. So starting from the back here, our laser generator is down in this cabinet. It's fully vented because the argon fluorine gas is some pretty gnarly gas. But the laser will generate out into this direction, hit a mirror down here called M1. This will deflect the laser up 90 degrees up to our M2, which is sealed within this box. One of the main upgrades from the Iridia beam delivery system is that it's fully sealed here. In other laser systems, it's not sealed, it's open to atmosphere, which is fine. But if you run out of purge gas, which is nitrogen gas, this gas is used to condition all the mirrors to make sure there's no damage throughout the life and throughout usage of it. You will degrade more with more air in the system. So this is fully sealed and fully pressurized system. So we go back to mirror 2, it hits another mirror here and deflects from vertical to horizontal. We then go through this lens right here. It's a little tough to see, but this is a homogenizer. It's a spinning aperture that homogenizes all of that beam's energy. We then fly down the beam path into this orange box. This is vertical in the Iridia. In the G2, this is a horizontal. This is our mask. The mask is, I don't think you'll be able to see it, but it's a thin piece of aluminum that has different size holes punched into it, which allows us to increase our spot size, decrease our spot size, and also just test how the laser is ablating at the sample surface with a series of squares and crosses and whatnot. And so how this works is that we simply just slide up that the mask into the beam path at whatever diameter spot size we desire. Typically in the E2 lab, we're running at a 20 micron spot for uranium lead. Zircon analyses for trace elements will go up to a 30 micron spot. In the new lab itself, we'll be at 40 micron for hafnium and 20 to 30 for uranium lead analyses. After we go through the mask, we then progress through the attenuator. We don't use the attenuator in any of our laser systems. This is for lower energy samples. But once we pass through the attenuator, we can then go to the front of the instrument, which we hit mirror 3, which deflects the horizontal beam back down vertical into one more mirror apparatus here that enters into the cell. And so the difference between the Iridia and the G2 system is the cup that Yanling showed you is on an arm that moves in and out from the cell. What we have here is this Z prime device. We have a little bit too much light going on in there. That's a little bit better. But this Z Prime device is its own module in there, and it has the mixing cup built into it. It's still difficult to see. There we go. So this little glass window is our mixing cup, and it has the same vortex effect that the other cup has. But the power of the Z Prime is that it is adjustable, moving up and down. They call it a dynamic Z over your sample. And so in the G2 systems, the arm is moving over your sample, whereas here, the cobalt cell, which is this big blue box, the stage and all of your samples move under the cup to collect analyses. And so again, just like on the other systems, we need a way to get all of that sample out. And so we have our sample line here that is moving super, super fast. It's the Eris peak tubing. This moves sample way faster than having a larger diameter Tygon tubing. And so the reason we have this laser is to do a couple of things. First, I want to just show you guys some of the pits that are coming out of this laser. These are unpolished pits that we have generated. So this is a 20 micron pit. I know I'm a little bit low, but this is a 20 micron pit. This is, you typically are at a drill rate of, I think it's, what is it? A micron per second. This is a 15 micron deep pit for 20 micron in diameter. And you can just see the quality of this. We have very steep, straight walls. There are no aberrations on the bottom, and our rim is having very little buildup of material. You can see there is a little bit of a brittle nature when we have this large excavation of material that is being partially analyzed at the ionized at the sample surface, which kind of makes this molten plasma-ish rim deposit. And then if we look over at this image here, this is just a series of spots on one of our standards. And this is now looking straight down, whereas the image before was tilted at 45 degrees. We typically take pit images once a month from both of our lasers, or whatever lasers are coupled to our mass specs, just to check pit quality. Because just like Sarah mentioned, the pit quality is huge for really, really precise, accurate data coming off of laser ablation systems. And so if we look down at these pits, the things that I look for poor ablation are very angular sides. So if you have a wider diameter at the initiation of the ablation, and then as you drill down, you start to make a cone, that doesn't look good. I'm also looking for little spires that may or may not be on the sample at the bottom of the pit itself, and then any kind of corrugations or wavy textures at the bottom. So from this series of pits, we can just we can immediately see that this laser is doing exactly what it should be doing. It's coupling fantastically with zircon. We have run this laser and all of our lasers over several different accessory minerals with rather good success. But the real main component of this Iridia system is its mapping capability. And so this is a image of a zircon. It's going to go through just a series of elements we have here. The first one, which just went through, is the actual CL of that grain. This is a complex grain from the Catalinas, and you can see it has several different domains. And as these maps are moving through, which are fully calibrated, fully background collected, fully quantitative concentrations for a series of different elements run off of this laser. That is the true power of the Iridia, is to make these elemental maps that are fully quantitative and use those ratios to create age maps, or to get at really, really tiny, tricky accessory minerals, particularly monazite, titanite within thin sections. They're very thin grains, and if you ablate through them, you have a couple of seconds on peak, but then you lose that signal rapidly. So the power of this mapping capability of only removing about a micron of material, but still getting really powerful, really fully quantitative data out of a small sample size is the true power of this. And so I'll let this kind of loop, but that's what I have for the laser systems here at LaserTron. We're looking to move forward with the Iridia as our full-time laser on either the new or the Element. And we'll keep you posted with more fun images, and hopefully coupling the Iridia maps with Zach's new Raman and EVSD setup in the SCM should be a lot of fun. And so I think we are going to send you over to the Element 2 lab with Wei Allen here next. But again, if there's any questions on any of our laser systems or the Iridia in particular, because it's the newest laser out on the market for geochron based and geoscience applications, feel free to reach out.
Hey, thanks, Dan. Can you all hear me?
Yes, we can hear you.
Oh, great. Hi, everyone. My name is Wei Allen. I am a postdoc at the LaserCon Center, and I'm also a minder in the E2 lab. And if I can just flip my camera really quick, I can show you what that looks like. So we started at the beginning of what it would look like as you walk into the lab. What you can see here are a couple of the computers that we use for data reduction, as well as offline picking. And what we can see here are a series of computers where we can actually see some picking of sample undergoing. And what I can show you what that looks like is that when you come here as a visitor, you have the opportunity of placing individual spots on individual grains. So this is an example of a tridal mount. And what's really nifty about this program Chromium that works with our laser, which is also something I'll talk about briefly, it's also a G2 laser that is similar to the laser you just saw in the new lab. What we can also do is use all of that important imaging that you may have acquired from SEM lab, which would be including CL imaging. You can actually overlay that and actually look at individual grains at their specific types of zonations. And from that, you can actually just go ahead and place different spots. And it's really just as simple as grabbing a little circle and placing it on an individual grain and going ahead and moving forward with that type of iterative process. And I'll briefly talk a little bit about the actual setup here. Here we have the laser itself. So again, this is the same G2 laser that you just saw at the new lab. And right now, what's being analyzed is a tridal sample that is a part of this overall analysis that's happening this week. And with this current laser or this current mass spec that we use is actually a little bit different than what we have been using in the new lab, where this Element 2 mass spectrometer is a single collector and not a multi-collector. And if we actually look inside the housing, and as you can see here, the housing is actually boxed in. You don't actually get to see the overall large bending of what we see in the new lab. What we can actually see if you look at a really basic map is this. So this is what is within the housing itself. You can actually see parts of the where the sample actually enters the system here. And from here, this is where the ion generation and plasma interaction happens and enters the system here. And this is the next phase where you actually get more focusing and lens capabilities here. And this is where the actual sample cone interaction would happen. And as the sample is traveling through this mass spectrometer, what the sample will actually interact with next is more or less the magnet system here, where you have this little bend in the arm. And from that, you would actually have the interaction with a conversion dynode, which is essentially a little metal sheet that ions are interacting with as they're being supercharged. And from that, there's a cascading effect that occurs that is actually being measured by an ion detector. And from that, we can measure the different amounts of counts that are occurring. And from that, integrate that into how we look at your samples. And if we move back over here, we have a series of different computer setups here. We have a computer that's set up specifically just for the laser. We also have a computer that's mainly just for recording data from the mass spectrometer. So there's two isolated systems where, as Sarah mentioned earlier, that there's actually a dance that happens between the laser system and the mass spectrometer system. And from that, we have different parameters for the types of analyses you may be interested in. So right now, there's the tridal mount that's aimed at analyzing 315 grains for uranium lead. undergoing right now, and this is the live analysis of it. There's this pit being ablated, and right now it's on a SL grain. And for the standard grain, what I'm interested in as a reminder is that I'm really interested in the overall counts per seconds and the overall intensity and peak shapes as analysis is ongoing, and really keeping track if anything is deviating from what is quote unquote normal. And what's really fun and interesting about working in the ET lab is that you as visitors have an opportunity to get to work with the mass spectrometer computer itself, as well as the laser computer, in the sense that you get to do cleaning shots, you get to control the laser itself to select your spots and actually place them precisely where you want them to be. And you get to also run the mass spectrometer computer to actually start the sample collection as well. And I guess what I can show you as well is a recent analysis that just happened early this morning. This is some recent data that was just collected, and part of my job as a minder is, again, as Third had mentioned earlier, is to look at the overall behavior of standards. So on here you can see some FC grains, some SL grains, and R33 behavior. And I'm interested in the overall fractionation plots, as well as their how well they plot on Concordia. And before I wrap up, I also wanted to point out that this is the LaserCon Center main page. So if you went to a Google site and looked for this page, and once you get here, and this is mainly if you're really interested in doing analysis at LaserCon, what you want to do is actually go ahead and go to the right-hand corner or right-hand side of the page and scroll down. And what you'll see here are actually the different calendars and schedules of the different labs. And what you want to do, say that you want to do analysis at the E2 lab, is that you want to click on the E2 calendar. And from here, you'll actually see the overall suite of different visits that are occurring. So right now we're looking at October. And what you'll actually notice is that as you pan forward into November and into December and into January, is that you actually have a lot of visits that are already being planned ahead. So what I'm saying with this is that it's really important that if you are really considering doing analysis here, we're really busy all the time. So it's really important for you to reach out to Mark or Dan to start planning those visits ahead. And I guess the overall process when you do book a visit here and you are prepping to be ready to visit, you'll actually get a live page here where you'll actually get a nice link to all of the information that we're going to need to work with you as you approach the lab visit. And what will happen is that we'll actually create a Google Drive link for you. And from this, what is really nice for us is that we actually get to keep track of all the different sample names that you have, all this information about how you want your sample process. So a lot of this information with like JC and PV, these are all if you sent us full rock samples for us to process for you. But if you just sent us zircon separates themselves and wanted us to mount them, we can also do that as well. And we'll assign them an individual mount number. And you here can delineate if you want DSC or CL done and what type of analysis and number of analysis. And as a minder, this is really important for me because it helps me understand the level of priority that you have. And even in the notes here, you can also note that you want to prioritize a certain sample right away. And it's something I'll keep track of as a minder. And I think that might be all I have for now. Yeah. If you have any questions, feel free to let me know in the chat.
Awesome. Thank you guys so much. Do we have any questions for the lab folks? Okay, if you took nothing else away from this, take away that they're all enthusiastic